Welcome back. Our next presenter is Luisa Still from Fraunhofer FKIE to talk about how acoustic sensors can capture two distinct sounds associated with a gunshot and use them to approximate the location of that shooter, which is very helpful in an urban setting. Luisa?
Yeah, thank you, Larry. Hello, my name is Luisa Still, and I'm with the Department of Sensor Data Fusion at Fraunhofer FKIE. And I'd like to thank Larry for the opportunity to present our work today to the worldwide press. My talk is about performance prediction for shooter localization in urban environment. And acoustic sensors can help increasing the security in an urban setting when capturing the muzzle blast and the supersonic shock wave of a gunshot. And afterwards, we can use the measurements of the muzzle blast and the shock wave to detect the shooter and to estimate the shooter location. This can be helpful, for example, to alert emergency centers in case of a gunshot or to help to arrest the shooter. Performance prediction is very helpful before the mission, so before the measurements, to plan the sensor setup that is needed to observe an urban district. And it helps in answering the questions, how many sensors do I need, which kinds of sensors do I need, and where are the optimal positions for my sensors. While doing that, of course, we have to keep the urban challenges in mind, such as sound reflection, refraction, and absorption. We use an information theoretical approach to predict the localization accuracy when detecting and localizing a shooter. And the inputs for these calculations are the sensor-to-shooter geometry, the shooting direction, the environment, for example, urban buildings or free field conditions, the sensor characteristics, and additional geometric consideration. The output of our calculations, the actual prediction, is an ellipse-shaped area. So you see this example. Here we have two sensor systems. This could be microphone arrays, and we have a target positioned here. And considering the direction finding accuracies, the sensor characteristics, we can calculate this ellipse-shaped area as prediction of shooter localization accuracy. We performed this performance prediction and compared the results with experimental results from a free field measurement campaign. So here we had a shooter located here. We had our two sensors, which were two acoustic microphone arrays, which captured the supersonic shock wave and the muzzle blast of a gunshot. And based on these measurements, we were able to localize the shooter. The shooter performed 5 gunshots. And I hope you can see the blue dots here in the figure. The blue dots indicate the estimated shooter localizations, and the red ellipse is the corresponding measured performance, while the green ellipse is our performance prediction that we predicted in advance. And here in this figure, you see the results when we consider only the sensor 1, this one. And here you see the fusion results of the measurements of sensor 1 and sensor 2. And you see that in both figures we see a very good match between the prediction in green and the actual performance in red. The ellipses have very similar sizes, shapes, and orientations. That means we have a good match between prediction and experiment. Then we performed an additional experiment, this time in urban environment. We had again our two microphone arrays positioned at these two positions, and we had a target positioned here. This time the target was not a real shooter due to safety restrictions, but it was a propane gas cannon which simulated shockwave shot-like explosions. And again you see the measured performance here in red, the performance prediction in green, again for sensor 1, and fusion of sensor 1 and sensor 2. And again, we see a very good match between prediction and experiment. You can see that because we have similar sizes, shapes, and orientations for the two ellipses in both cases. So now that we have validated our performance prediction and observed that the prediction gives us a very good hint of how the actual performance will look like, we can use the performance prediction in advance to evaluate a specific sensor setup and to see if it is good to observe a specific urban district. So here I have an example. You see the dashed lines, these are the urban buildings. And here in this setup, we have one acoustic sensor placed here in the middle. And the yellow areas are blind spots of the sensor setup. That means if a shooter was located in a yellow area, we are not able to localize him with sufficient accuracy. That's why we would recommend a second sensor. And in this figure, you see here we have two sensors, and the complete area is blue now, which means we have no blind spots. And two sensors are sufficient to observe this urban area. Yeah, and with that, I'd like to conclude my presentation, and I'm open to your questions.
Thank you, Luisa. That was very informative. A couple of questions that come to my mind immediately. One, how long did it take from the time of the shooter to the pinpointing of where the shooter was?
This is actually really fast. It's close to real time. I think maybe from the shooting event to maybe having the pinpointing on a map, it's only a few seconds.
Okay, so that is effective if you're trying to actually find somebody, so they don't get a chance
Yeah.
to run away. Does the height of the sensor array matter? Did you examine that at all? Like if you put the sensors on the ground in an urban setting versus on top of a building?
Yeah. Yeah, that's a very good question. We did that. We in this measurement that I also showed you, we had different sensor heights also on the building, but we still need to evaluate the influence of the different heights.
And you talked about an urban setting and buildings in particular. How much havoc do the buildings play on the kind of acoustic sounds that you're trying to detect?
Yeah, the buildings have a huge impact on the measurements. We were able to measure reflections from the buildings. So even in line of sight conditions, the building severely impact the measurement. But in line of sight conditions, they can even be helpful to localize the shooter. And of course, in non-line of sight conditions, the buildings make the localization much more challenging.
I can imagine.
Yeah.
We have a question from the web.
Yeah, so do other sounds interfere with these kinds of sensors? Is there any worry of false positive signals?
Yeah, very good question. Of course, other sounds, other impulsive sounds can interfere, but we are also working on classification methods, deep learning-based methods to help to distinguish between actual real gunshots, which have a very very characteristic signature, and other false positives or other impulsive sounds. Yeah.
Okay, great, thank you. And then out of curiosity, I know this is meant for an urban setting, but is this kind of concept and idea extendable to schools or inside of buildings?
Oh yeah, very interesting. Yeah. I think inside environments it would be even more challenging, but of course that's a very interesting application, and I think that would be applicable, but very challenging.
Okay. Any other questions? Thank you so much, Lisa.
Thank you,
It
Larry.
was very interesting.